Hello and welcome to another video in we talk about the anatomy of a problem. In the previous video, we talked about drawing a house and how a computer has a really hard time kind of drawing a house because of the nature of the problem it is. And in today's video, we're going to talk exactly about the problem. So we're going to go over some of the problems and we're going to kind of understand how not all problems are built the same. So we're going to try to get groceries again from the store. And I have like a few instructions for you. So number one is get groceries, right? Get groceries. And then it's like get groceries from a store. Get groceries from Target. Get groceries from a Target in a car. So as you can see that the top get groceries has so much flexibility. Like you can get groceries however you want, in a car, in a bike, in a plane. You can get them from Target. You can get them from Walgreens. So the problem is the flexible the decision making is, and humans are good at that, but computers absolutely suck at that. Same thing with like really traditional robots. You have to be very precise if they're kind of navigating in a space. Then again, get a loaf of bread. You didn't even ask what was on the grocery list. And the last one is like take 5 steps forwards, turn right, take 5 steps, reach the door, open the car door, handle below, and enter the car. So you can kind of see like if you sometimes program robots that are kind of not operating on like more machine learning focus, they have to be precisely programmed. So as I said, humans can handle the ambiguity, but computers have a rather hard time. So you might have seen your computer crash at times, like Chrome crashes, like it crashes a lot for me. And it probably is because a computer has to make a decision which it doesn't know how to, and it kind of crashes. It's kind of like sometimes a memory leak, or some things are not properly written out, so it kind of crashes the system. If it was smart enough, it would know how to fix it. Like a student of mine also asked one time, like I'm like, oh, you have to put a comma between like these two, like in a function, two parameters, and she's like, oh, if it's smart enough, it would know what a comma is. But then again, it's very interesting. Like a car won't move by itself. It's just like you have to control it, unless it's like a Tesla with FSD. But you kind of get the point. Like machines are kind of built very differently. So how does a computer normally make a decision? Well, we program it initially, but a computer indiscriminately runs everything. So you basically run code that gets compiled into like some sort of an instruction set, and that just runs like a computer chugs the whole thing. Like it doesn't even think about it. It just runs everything. You remember like killing it? Like it won't. So how do you make like sometimes something run? Like if a program runs from top to bottom and everything runs, what you do is you basically kind of add this thing called a control logic, which is kind of if-else statements, which if something is true, this part of the code will run. And if it's not true, this part of the code will run. And that's how you basically go from top to bottom without running certain code. And in assembly, it kind of translates to jump, like it jumps to a particular line of code or the instruction set. So you can kind of see the example here. A computer is very basic, very simple, like very simple person. So if you were kind of talking about getting groceries, it will look like a little bit like this. So this is just leaving the store, right? So face direction, exit, take N, step forward, turn body. And these functions are already programmed. So imagine if you had to program everything all at once in one wrong direction and you're kind of stuck in the store forever. So those were like physical problems. And now we're going to talk about like digital problems. And that's kind of where the AI agent will... It will come. Just be patient. So let's say sort a list of contacts in ascending order. Find and replace all the instances of color with color in documents, because we are British, aren't we? So diagnose and resolve any incoming employee tech support issues. Sorry. So think about these problems, like get groceries from somewhere, things like that. So spoiler, like as you're kind of going down, the decision space is getting really complicated. Create and run a game involving a turtle. Like what kind of game? Like, it's like so many things. So how would a control logic handle this? So there is no control logic in terms of sorting contacts. It's just basically sorting things. But if you look at diagnosing a problem, you can see the control logic here. So if slow, computer issue, categories performance. If categories performance, checks disk space. So you kind of have to like kind of program all the decision space out of how the computer will make a decision, and it gets really, really complicated. And I'm going to tell you how complicated the decision space gets. It's in the trillions and zillions, because of how many permutations there are. We'll talk about that with a very cool looking graph. Okay, I'm kind of being a little bit over the top, but we're going to see how it kind of exponentially increases. So LLMs, which are kind of a little bit more sophisticated, more flexible reasoning compared to a CPU. So basically, you will give it an input, which would be like current ticket state. So it's like, okay, free disk space is 7%, high CPU process present equals false. What should I do next? It will kind of give you an action pretty much simply. So the decision tools, or like what to do, can increase, but the control logic will kind of remain the same if you're using an LLM, which I'll show you. So here, basically, you have the performance actions. And if you've done LLMs, you know how they work. So basically, we're going to pass the state, which is going to look a little bit like this. This is an example of an example state. And then you're basically saying a prompt. You're a troubleshooting agent. And these are the allowed actions. And this is the state. What do you think I should do? Like, that's an LLM, right, basically. And it'll basically respond with, like, an action. And then you basically take the action and then basically run that. As simple as that. So instead of like if else, you kind of just basically have this, and it can look at the generalized information it's gotten from like all of the web, and use the power of LLM to kind of add that. So this is kind of like the first part of where the sensibility of like an LLM comes when we're thinking about agents. Okay. And you can see that basically it gave you the task, which was like the next action. And then you just basically run that function. And that function is already programmed. And we're going to talk about function calls and tooling, which are a very important component of agents. But you kind of have to bear with me on that one. AI agents are kind of like when LLMs and programs have a baby. LLMs bring a dynamic logic to the program. So that's one part. In the next unit, we'll kind of explain more components of what AI agents are. Like, we're going to try to like build a game, and we're going to see like what are the things needed, like what is a state, what are the loops, what kind of function calls are we needing. So this was basically the anatomy of a problem. We try to understand what a problem is, and how a computer makes a decision, and how a computer runs certain code, and how to create a dynamic logic control from an LLM. So in the next video, we're going to talk about the anatomy of AI agents, which is a very interesting one. We're going to build our own agent as well. Very simple one without frameworks. And now I think you're kind of understanding what an agent is, and like what is the autonomous nature of the decision space and things like that. But yeah, until next video.